Okay, so where we are at is the fundamental spaces. Okay, some people call them subspaces. There's a reason for that. They're not always subspaces. And in fact, that's the thing I want to hit on today, is what are these things? And so the main thing we've been using is an example, but the point is it actually applies to anything that's a linear transformation. So I'll remind you that we have vector spaces. We don't bother describing what a vector is. That's not really helpful. But we can describe what a vector space is, which is how do vectors come together and interact, okay? And so it's usually denoted by a big letter like U or V or W, things like that. And the things inside of it get to be called vectors, and it comes with an addition and a scalar multiplication. And then there's a few sort of ancilla. There's a zero vector. Maybe you put a hat on it if you want to distinguish it from the zero scalar. I won't do that long term, but at times it helps. There's also negatives, so that I can subtract. It actually turns out you don't need all of this information. It comes along for free once you just have this addition. Then repeated addition gives you scalars by n and by fractions and so forth. Nevertheless, it's okay to assume you have it in a vector space. And so we'll sometimes write this as a big, giant tuple. Just a weird quirk of mathematics is that when you put parentheses around data, you can say 1, 2, 3, then all the data inside are the same type. They're all integers, all decimals, or whatever. When they're a mixture of heterogeneous data, we use these angle brackets. Okay, so it doesn't mean less than or equal to. It's just a fancy parenthesis to gather data that we want to infer goes together but isn't all of the same class, the same type of information. Okay, so that was just an illustration of the differences between them. So I have a vector space, and then what I want to do with a lot of situations is that I'll have two natural problems that already have vector spaces, two or more. And I want to collectively understand how they interact. So we had been using one story problem from a business model, the Nabisco problem, which was, and that's going to be my archetype for the rest of this, plenty of other examples, but it's just a nice archetype that makes me feel hungry. So I'm going to go with it. So we were combining three vector spaces in the Nabisco problem. Okay, remember hexagon with a y, you've got yourself a cube. What are the three spaces we've been combining, the three vector spaces we've been discussing over the last couple of lessons?
Client orders.
We have the sorry, what was it?
Client orders.
The clients, is that what you're saying? Yeah, clients?
Yes.
I'll call it C, I don't know, C for clients. That's the orders, right? The orders that the clients are making, the requests they make of our products. You can change that around, right? It could be you're a manufacturer and you don't have clients, but you just have products that you produce, right? You could be a web server. What are the things you serve out, right? You could be a bakery. I don't know. Imagine anything you want. Anything that has a production model behind it, it's probably got a vector space behind it. Okay, the next thing is we have the plants that actually manufacture it. So P for plants, that's a vector space of where we build the things. And then we have the supplies, or sorry, in this case, the things we were worried about weren't the supplies, but the schedule. You could also think of ingredients. Do I have enough baking powder? Do I have enough flour? All those things could go into a vector space to make this a four-dimensional creature that explains all of those features. And the real life story problems do study it this way. When you study a problem related to creating a schedule or creating a way of distributing information, this is often in business circles called logistics. And you can search that up and find business people talking about logistics. The mathematicians and the engineers call this linear programming. Okay, so it's just a matter of knowing who you're talking to. If you're talking to your manager, you mention the logistics. If you're talking to your engineering team, you mention the linear programs that you're working on. Okay. Okay, so we have these data, and then our goal was to somehow explain how we're going to relate all these vector spaces together. And what we have is this sort of box, which we think of as, this is usually called a tensor, okay? And it has to have convenient properties in terms of, well, each vector space comes with this tuple of other information, right? Every pair of orders could be added by whatever adding orders means. Every plant could be combined by adding, rescaling, so forth. All of those operations exist independently in each of these vector spaces. And so as a result, the features we need is that the data distribute, meaning they play along well with the addition. So now let me do this. My backup camera will shift to the side. And so now what I'm going to try to do is articulate without worrying about the story problem. I'll still mention it as I write it. I'm just going to articulate what's going on with the relationships in order that we can do linear type things. So let's give this tensor a name for the description of all the things that are going on here. There's a tradition of calling this a capital gamma. Okay? Capital gamma has a strange, or what do you call it? Like there's an advantage it has as a letter, which is that there's kind of this little indentation under this little, rain cover, right? So you can park your bike under there and it doesn't get wet, right? And the bike is IJK. It is telling me which client, which plant, which schedule, okay? So whatever you have, you want to sort of pack all those indices as subscripts because mathematicians prefer subscripts. If you program, then you might just write the word gamma, and it would be some sort of an array. So you'd say I, comma, j, comma, k. So don't get too hung up on this, but the nature of this, the letter gamma being advantageous for shifting that information inside is why it's stuck around, okay? Just for the sake of camera visibility. That thing doesn't need any oil. Okay, so I don't mind using the boards, and once I know echo is working, that's what I'll do. But for today, I'm just going to actually minimize camera work by just moving the boards around, okay? Okay, so this is the way of describing the actual data set that's relating my three vector spaces around. Now, what's the distributive idea? The distributive, when we discuss it on a story problem, we have to think, why does this story distribute? For example, why can I schedule independently for each order? That was the distributive property of that schedule. In this situation, what we need to do is think about how we're going to use this gamma. So this gamma, I'm going to put it inside a little bracket again because I'm mixing different kinds of data. But what I'm doing with this bracket notation, for those of you who've seen tensors before, this is what's known as tensor contraction, and if not, you're seeing it now, okay? We are going to stick in no longer just IJK, but combinations. And the reason we want combinations is, well, we thought we wanted a linear problem after all. So we should be adding vectors together, we should be adding coordinates, mixing them. So I don't just want 1, 2, 3, I want 1, 2, 3 plus, right? I can have 1, 2, 3 plus, say 7 times 1, 7, 2 or something, right? That's the kind of data that I combine when I'm trying to say, like, does my story problem distribute? Well, I have to have some combinations to think about whether it distributes or not. So what we're going to do is that we're going to take things like this and focus on the fact that that has a secret hidden number 1 there. And I think of that as like a 1 and a 7 and so forth, right? I can start to combine these as vectors. All the different combinations are going to be written like this. But I have to somehow keep track of those numbers, okay? And so what I'm going to do is back off for a second and go back to a good old-fashioned two-dimensional setting. Make sure I track what that wants me to do, then I'll bump it up to the general setting, okay? So I look at the rows of any kind of data set I have. And I have a matrix, I have rows, I have, each client, right? And then I have columns of all kinds. So each column divides this up in other ways. The rows and columns do not have to match in size. It's a rectangle. Okay? One of the ways that I can look up a row is I can just say point at it. There, right? But the problem is sometimes when I want to talk about 2 rows at once, I'd have to do that, right? I have to point to 2 rows at once. And then maybe what I want is to actually take their average. I don't want row 1 and row 3. I want half of row 1 and half of row 3. So then it's kind of like I half point at them. It should be a better way. What I'm going to do is I'm going to scale that one by 1/2, scale that one by 1/2, and then put zeros on the ones I'm not using. I just put the proportions of each row, and I just stack them in front of the row that I'm using, right? And then this gives you kind of a mechanical way to think about it. Because what I'm going to do is distribute this 1/2 over all of those coordinates. Just multiply by 1/2. Each one of them is a number. I can multiply them by 1/2. Distribute that 1/2 all the way through. Do the same thing with 0. Well, that one happens to be very fast. Just write 0 in for all of them. And I do this through every single row. What will now happen is I no longer have to worry about these scale factors. That's now factored into the new set of results that I have. But I still haven't actually combined them, right? I haven't added anybody together. So what do I do as my last step? I'm missing the addition, so I should add them, right? And so one way to do it is to sort of, think of your good old-fashioned, there's nothing wrong here with thinking about old-fashioned stuff like this, right? You just stack numbers and you add them. Just think of these as a bunch of stacks of numbers to add. Add in each column, right? Stack, 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 add, add, add. That will create a new row, not in this table, of rescaling everybody and adding them. So in this particular case, 1 half 0, 1 half 0 is going to produce the average of row 1 and row 2 in each coordinate. Is that clear? Does that make sense? Okay, this is a, let's call it a row contraction. I took the rows, I rescaled, and I contracted them. I used to have 4 rows, now I have 1, right? Now, what if I wanted to change what I wanted to worry about? What if instead I wanted to work on the columns? Can somebody come up with a clever algorithm? Anton.
Write the numbers on top and then do it.
Precisely. Just put the scalars on top of the columns, distribute those scalars all the way through each column, and then which way will I add? Okay. Now, set this to the side for a second. Get my little workout in today. I don't think they're slate. I think they're actually porcelain steel, but they are not on greased wheels. I think nobody in this room teaches with them, is what I'm discovering. So, I've had some slate boards, and I don't think you could even put them on wheels. You'd have to have a little winch system. Okay. Some of you have seen matrix multiplication, am I right? Okay. So let's try to convert what we just did into our standardized matrix multiplication. So I took my table, my data here, and what I did was I put numbers on each row and spread them across. All right? How would you modify that to make it matrix multiplication? Because right now, if I just put that here, are these the kinds of things you draw when you do matrix multiplication? Because the interiors are not matched up, right? Something's wrong here. So what would you do is you would tip this over like a row vector and then write it in front of the matrix, okay? That is done primarily for reasons that do not matter to your life today, okay? It is done as a kind of historic, get people through World War II kind of thing. There was a lot of linear algebra that was optimized during the World Wars because we had people in trenches doing calculations by hand, so it was just get a formula to them. Teach people quickly. And now we have machines that do a lot of this stuff for us, and we can pause and say, is this how we need to learn it? So the idea of tipping over is because when you're doing manual calculations, this turns out to avoid having to swap things. Imagine if you just built it like this. Then the next one would maybe come out of the board and so forth. You end up with 3D models in your head or higher dimensional models. It's hard to write that down. So if you always tip, then you can keep things going in a straight line left to right. And that's the only reason to tip it over. There's no mathematics behind it. In fact, mathematically, a vector isn't even flat like this. The vector could be like this, right? Mathematics doesn't care about the shape of your vector because we only talk about the vector space, right? We care about how it acts with another thing. Write it however you need to, right? It's not the shape that matters. So the matrix shape, that conditioning here that you've been taught has nothing to do with mathematics, but nevertheless has to do with how other people think you're going to talk to them. So I'm switching it back to that standardized notation so that you can talk to other people, but don't perseverate on what this looks like or why. It's not a meaningful change, it's just a standardization, okay? It's like using inches instead of centimeters. It's a choice made, and nothing really happens with either one of these choices, except that inches is correct. Okay. This here and this here are now considered equals. It's just notation, but the way we think about this is that we think of taking this and rescaling the first row. This one rescales the second, that one the third, that one the fourth, so forth. Likewise, instead of putting the column scalars above here, what do we do? What's the translation to keep the same pattern going? Yeah, that one gets put in its flipped over. Now let's give this a name. When you make this transition from one to the other, this is called a transpose. And again, the understanding is you take the first one, rescale the first column. Second one, rescale the second column, so forth. And then you add along that way. So if you do this, it'll collapse into a column again. So the main idea, what do you see here, the persistence that's happened here is that if I multiply by a row, it ends as a row. If I multiply by a column, it ends as a column. That's the whole idea here, okay? These are two contractions, all right? Does everybody kind of, they feel like this is home base, I could do this, I had to do this. All right, now let's go back to our giant tensor, our Nabisco cookies. We want to explain what this is doing. We use this as a crutch to sort of think through how we might start combining. Okay. And so when we had a grid of numbers, which we might just call M for matrix, we could modify the rows with a U in front, a column that scaled the rows, and then we contracted those rows down to a single row. Or we might, so this was row up, row scaling, row contraction. We could also do the columns, and again, because we've transposed, the V goes to the side, it stays in a straight line. In my head, it really deserves to be on top. We're scaling the column pieces, and then we push those all down and add them up, okay? But nevertheless, that's the notation of today, is that we transpose it, put it on the other side. Okay, so maybe one of these should be transposed. I'll put a transpose on that one. That's a T for transpose. And that's the column contraction. Okay, I'm abbreviating so I can do whatever I want with the letters. Okay? But now we have a three-sided thing. So what would you think we need to add to this storyline? So if I take a box, you can rescale all the rows of that box, right? And now let's pause for a second. Do we really know what that means? We knew what it meant to just distribute it over all the things in the first row, but it's a box now. What's the first row? It's an entire sheet of paper. It's a plane. Like, think of it as a book, right? Where the first page, page one, that's that whole plane now. You now rescale everybody by that same scalar. Go to the next row. Rescale everybody by that scalar. Rescaling all of them by those scalars, then what do?
You hole punch, you add everything.
You hole punch. I don't know if I have a good kind of visual analogy. It's kind of like a sifting sand or something. You put it in a compressor, you squish it down. I don't know. You juice it. So no, you add up each one of those scaled pages, coordinate by coordinate, all the way down, and what will be left is in each coordinate will be a number. It'll be, maybe you could call it the average, right, or the weighted average of all of those numbers in that column. And the next one, 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 and the next one. You fill out the entire graph paper. Really think about it like a pad of graph paper with numbers written in all those little squares on each sheet of paper. Rescale them, push them down. Okay? That's our first. So we're going to modify from this to that. So visually, here's my gamma. There's my vector u. It's pushing through all the slices and adding them up. So it sort of contracts to a single sheet of paper. Okay, just scales each little sheet by U1, then U2, then U3, adds them up. Okay. But now that I have a sheet of paper, look what I could do next. The next thing I could do is that I could say, well, actually I also want to scale over here by some vector v, like on the columns. Again, I'm not transposing it like you do in matrix multiplication, because we have to give up on that serialization, writing it all in one row. This is three-dimensional. You're not writing it in one row. You're going to come up with some other notation, okay? So I'm drawing it the way that visually I think about it, because that's really what I want you to do, is mechanically understand how we're doing the work. So what should I do? How should I think of modifying my box of grid paper if now I've got a little strip along this side of numbers? You're all doing the right thing. If you're not doing this, then you're doing the right thing. If your hands are moving, if you're thinking out loud with your hands, you've got the right idea. And if you only can pretend that you're here, then I'm sorry, you're missing out, okay? I won't look if you're embarrassed. What's happening with the V? Go ahead, Matt.
Kind of think of the notebook as standing up this time.
Okay, sure. Slice it with the pages, you know, sitting on the bookshelf looking at you, and you rescale each page. Rescale by V1, V2, V3, all the way along. Okay, they're all rescaled. Now what's going to happen with them then?
Collapse that way.
Collapse, or in what's the operation I'm collapsing with?
Addition.
Addition. And what's going to be the result is some grid this way. Is there anything else we could do? Well, you laughed, so now you have to tell us, Parker.
There's one more.
There's one more.
direction.
There's one more direction. And there's also one more chalk color. So we're in business. Where's the other direction?
That like angular.
Yeah, so let's give these cardinal directions so we can start talking about them. That's up for y. You know, typically y goes up. This one might as well be the x. And so that axis will be the z-axis, right? Just to have a name for it. And I call these axes, and so do other people. We call them, actually, physicists call these the legs of the tensor. Because why not? So mathematicians call them the axes, and you can perhaps see why they're called axes to a mathematician. If you want to know why a physicist calls them legs, it's because they have what's called tensor network diagrams. They write a little circuit that says, look, all you really need to know is not how it's laid out in memory, but how to look it up. So you need an I leg, a J leg, and a K leg. So this little creature walks around with 3 legs. So that's not bad actually either. Intuition-wise, it's not bad to do this kind of drawing. But it's fun to make fun of physicists. So the z-axis has its own little vector. And I hope you picked up on the idea. We slice it along the vector, along the axis of the vector. So we get a bunch of parallel streams like this. Down, 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 down. And then each one of them is being rescaled by the corresponding coordinate, and we add in the direction of the axis. So we'll push out over here to a grid like this. So now we got to go back to our notation. When I want this one, all I need to do is tell you which axis the vector u is on. So what I want this one to be will be my tensor gamma contracted by u, but that's not enough information because I don't know where I put u, right? Imagine this was cubical. So the vectors could be on any side. They're all the same size. That would be insufficient information. So just like rows and columns, we have to disambiguate which one's rows and columns. And we do that for matrices by putting the u in front, that's the rows, the v in the back, that's the columns. If you're reading left to right, you only need 2 sides for rows and columns, that worked. For tensors, higher dimensional data, you gotta have more space, more sockets to put things in, so you need some notation to help you. So I just put a little y on the bar. And then I close the tuple. So I'm combining 2 heterogeneous pieces of data. One's a cube of numbers, one's a list of numbers, and I'm telling you where to contract. Good? With that notation, put in your own diagrams what this one is and what that one is. And then I will put what I think they are. Okay. Now there are variations on this notation. Everybody has the opportunity to make this notation worse, and many have tried. So in engineering circles, there is now this notation. And that's trying to be this one here. Only that would assume that in engineering circles it mattered to name the axes. It doesn't. So what they do is they name the index that they would use on that axis. Okay? Now, I'm not saying that's actually less guided. You can see the elements of the data here. It's very coordinate based, it's very matrix based. There's another notation. You could go back to just writing down what everything's actually doing on the coordinates. You could say, look, at the end of the day, what's going on when I do this is that I'm summing up the value of gamma I, j, k, v, let's say that this one is I, j, and k. So the j is going from 1 up to whatever the dimension of the x-axis is, like this. So now I have ij here. Okay? So notice what we did. We observed that the result was a grid itself, right? And we got rid of one of the axes. And so when we got rid of one of the axes, well then what we need to do is just keep track of 2 more indices. So you kept, oh sorry, that's not a j, that's a k. You kept track of I and k because those survived. And you contracted the j, so you put a sum from 1 to j, from 1 to the dimension of the j side. Okay? So this is what everything actually means if you have it in coordinates. So now, just to make sure that you are paying attention, here's the physics notation. This is called Einstein notation. If this doesn't make you question Einstein's brilliance, then yes.
I just had a question. I guess I'm having trouble understanding. So, like, why is the orange kind of plane there? Yeah, why does that use U? And
Oh, do you think I've matched them up wrong? That's entirely possible.
Yeah.
I probably didn't track my pictures correctly. Hold on. Y contracted this one. This one should be Y. So let's change this. I think what fooled me was the different colors I used at different stages in life. So now I'm going to be very careful, because if I'm confusing, we're all hosed. U contracts this way, leaving me with that picture. Are we good with that? The y-axis is gone. This direction in gold is gamma contracted now along the v side, which we declared to be the golden x. Does that seem valid? Then lastly, this was a w in the z direction, z and w, that looks correct to me. Thank you. Michael?
Yep.
Yeah. Okay. We're good? Anyway, so here's another notation that you will see. It's very subtle, but you see that there's a superscript subscript. And the idea is if one's up and one's down, then that's abbreviating a sum through the j's. I won't say that that's not somehow clever when you're doing calculations, but I will say the following thing. You better get your eyes checked if you're going to use this notation. It is incredibly easy to make a mistake by just not being able to tell what's a subscript on tiny, tiny fonts. So I find this very difficult to read. So that's just a comment, okay? Anyway, you will see this. If you're sitting there with a machine learning algorithm, invariably you're asked to do some kind of tensor contraction. You're asked to pick up some things. There's even these things called tensor algebra compilers. There's tons of them now. Sitting there on PyTorch or TensorFlow or your own homemade thing. And you're stitching together all these formulas based on how you want to move data from one place in your story problem to another. And it's a bunch of sums. It's really nothing deeper than that. But it's really complicated because the networking of which ones are coordinated with which ones is so hard to get right. So difficult to get right, okay? And everybody is trying to find a way to say, look, this high dimensional contraction business is what I'm trying to communicate to you. And so everyone's got their own pocket notation to help you with that. Some of them you'll get better at than others, okay? But get used to one or two of them because you will talk to other people in the real world with these data, okay? Now, with these in mind, let's now write the distributive law that I'm really talking about and go back to our spaces, our fundamental spaces, okay? So now what we have is we have vector spaces. I'm going to be coy about coordinates until later. We have a good place to talk about coordinates, but today, if you only understand the decimal numbers, that's fine. Think about those as the ultimate numbers. That's your R, your real numbers. If you've already moved on to include complex numbers, the square root of -1, even better. If these are too challenging, come back to Q. The rational numbers, that's fine. Actually, every real world application is just dealing with rational numbers. Floating point stops somewhere, right? They really don't have any decimal numbers that go on forever. There is no pi. So pick something. If you're on the more discrete side, or you see yourself heading there, pick integers modulo of prime. They won't let you down for this problem either, okay? But pick one for today. And if you know several, think about interchanging them. And that's your k. Every one of you can have your own individualized k. Can't have pi, but you can have k. So, all right? And then you have vector spaces that only take values in those. So every vector is a coordinate with values from your k. And we have several of these vector spaces, v1 through vl. And now we're going to try to describe this gamma thing. And what we need to know at the end of the day is here's gamma. And I really just need to tell you how to get away from gamma to something else. And we said we did it with 3. You could do it with L of them. So for illustration purposes, I cannot draw in 4D. My illustration is for L equals 3. Okay? Because it's better than 2, but not so far that you can't draw it. So here's what one wants to think about. You have your gamma, and you could contract it in the y direction, or the x direction, or the z direction. But you weren't done. Look, each one of those was yet another grid. So you could layer on top of that another gamma. And another contraction. And another contraction. So you could then go from here, maybe to there, right? You could also come out. You could go over here. And now you start to see a puzzle emerging, which is, hold on a second. Am I branching out and always getting new data? Or what if I went 2 different paths? Would I come back to where I started? If I start from here and I contract with the y and then the x, versus contracting with the x and then the y. Are they two separate results or the same? Try it with matrices. That's contracting the row side, if you remember, right? It says take the vector, turn it sideways, scale all the way through the matrix, add. That's contracting on the column side. Take the columns, scale all the columns, and add along the columns. If I do rows, then columns, that's this one. So that's taking my rectangle. First, I'm scaling it to the rows, which leaves me with one single row. Over here, I scale it with the columns, leading me to one single column. That's when I do both. And then the question is, so this one here, this path is this one here. Rows, then columns. What about the orange path? How would you write that?
The parentheses around that and the V.
Now, what do you know about multiplication?
It's associated.
It's associative. At the bottom of this, we're ending up multiplying what kind of numbers? Things in K, right? Do any of these care about the parentheses? They do not. The whole point is that because your K has nice properties, that bubbles up and becomes an emergent feature of your larger system. Your tensor contraction is also associative because the multiplication was. In fact, the tensor contraction is also commutative, which is actually the name we give to a square like these days. We say you can commute on any path and you get to the same place, then you say it's commutative. So even though this looks like the associative law, the only reason it looks associative is because we thought about left and right being on separate sides for rows and columns. Let's convert it to our gamma notation. Our gamma notation would have said, look, there's a y-axis with u, and then there's an x-axis with v. That would have been the exact same notation in gamma in bracket notation. Okay? And on this side, what would you have written? For the orange, you would have said, instead, first I'd like to contract the x direction with v, and then I'd like to contract the y direction with u. Does that seem fair? And so now if you stand back and look here, the gamma never moved. Who moved? The u and the v swap places, right? And so this is more like commuting, if you know those laws from some algebra class. So these days, although the associative law is drilled into your head from matrix multiplication, you can more or less set that to the side and never use it again. We just don't have associative multiplication because we don't put things on different sides when it comes to tensors. Matrices are this lone wolf where for reasons of history, we sort of stuff stuff on all sides, okay? But now we can't imagine writing it at that scale, so we just put everything on one side and index where it's at, and now the order doesn't matter. Okay, the same thing's going to happen here. Let's write one or two of them. So for example, we could write this one like this. We could say gamma of ux yv. So that would be, say, I go ux and then y right here. That should be equal to, what do you think? Yeah, just swap the two, right? Put the y first, and then the x. Okay? Now, if you practice this long enough, what do you come up with? Is you come up with this idea that actually maybe I don't need that many brackets because the order isn't really a problem here. So there's a shorthand notation. Put a single bracket, contract x and y. But now because we're going to lose track of who's x and y, we don't even bother putting it there, we put it on the vector itself. Okay? That way we know this one goes on the x side, that one goes on the y side. And now we don't care, just put them in the order you like. Can everybody follow this notation, what I'm doing? I'm trying to describe how it is that I'm going to get a lot of different complicated vector spaces to talk to one another. I'm going to bring them together by this thing called gamma. And then when I want to evaluate them in combinations, instead of input and output, I just give you all the different ways I want to combine them. They come out as a number. I can see I'm not going to make it all the way to spaces, but I will get at least to the general distributive property that I wanted to get to. So in this new notation, gamma starts out, and it now has slots for 1 through L. And it doesn't really matter where you put them as long as you put which slot it goes in, right? And they don't have to be 1 through L. They could be X, Y, Z, or A, B, C, or client, supplies, and plants, right? Whatever the axes are to your story problem, call them something useful for yourself. I'm going to use 1 through L because I don't know what problem you have in your head. All right? Distributive law. Distributive law, distributive law, distributive. That looks like multiplication parentheses, right? Are there any parentheses here? Are there any parentheses here?
Fancy one.
Yeah, there's fancy parentheses, but that's not a problem. We can deal with fancy. We're semi-fancy people. Look at us in our shorts.
Thank you.
Okay. There's a plus inside of some parentheses. Thou shalt distribute. Now, what am I really saying? What I'm really saying, and we'll stop here. I'm really saying this. Here's my first box. Here's U1 that I'm rescaling on that side. Here's that same box. Here's U1 tilde that I'm scaling on this side. And when I add them up, sorry, I'm adding the opposite direction to normal addition. That's just lack of planning, right? This should be that way going down, but nevertheless, hopefully you can handle this. It's saying, actually, you could have added them together first and just done one contraction, right? And in fact, should that not also work in the U2 position? And the U3 position, the U4 position? This is now the general concept of tensor contraction. You have something that you can commute in any direction you want, and every single contraction distributes. We'll pick up on whatever the next day is of class, and we'll describe the fundamental spaces for these.
That's the best thing I can.
That's a good one.